Hi. Today we're talking about LeetCode problem 2151, maximum good people based on statements. So this problem can be a little bit of a mouthful to describe, but let me try to walk through it. Basically, we're going to be dealing with people, two types of person, a good person who always tells the truth, and a bad person who sometimes tells the truth and sometimes lie. Bad people can either lie or tell the truth. With no real restrictions on them. So our people are going to be making statements, and the statements they're going to be making, they can make one of three statements. They can say a person is bad, which is represented by a 0. They can say a person is good, represented by a 1, or they can make no comment about a person, represented by a 2. And so what the problem asks us to do is write a method that's going to be given a two-dimensional array of statements. And so the two-dimensional array works where the first axis of the array, of the two-dimensional array, is going to identify what person is making the statement. And the second axis is going to specify what the person, or who the person is speaking of. So a coordinate in our two-dimensional array might be 0, 1, and what that would indicate to us is that person 0 is making a statement of person 1, and the statement that they're going to make is going to be a 0, 1, or 2, representing those three statements I just defined for you. So if our example is 0, 1, and the value stored there is 1, what that means is person 0 says of person 1 that they are good, meaning that the person tells the truth all the time, which I guess is the definition in this problem of good person. So the problem says, I want you to write a function or a method that takes this two-dimensional list of statements and returns the maximum number of people who could be good or who can be good based on the statements made by the n people. So I think there are kind of two key things to solving this problem, or like two things to realize. The first thing to realize is that bad people basically give you no information. Because there's no restriction on whether they're lying or not, a bad person is basically like a random statement generator. The fact that a bad person says somebody is a liar or truthful, that doesn't inform you at all. So basically, statements made by bad people, we can just ignore. Or in other words, we only care about statements that are made by good people. And a little bit more specific than that is only if a good person is saying something definitive, that's the only time we get information. So remember, people can say no comment, or they can say, value 2, no statement is made. So if a good person is saying no comment, that doesn't tell us either way. So the only information that we get comes from a good person making a definitive statement, either a 0 or 1. So that's one realization to have. The other realization, I think it's often helpful to do this, is to look at the constraints of your problem. If this were a job interview, you might just have to ask, what size of inputs are we going to be dealing with? Because that's going to tell you something about the answer. So here, under the constraint section, it says that n, which is going to be the length of our statements array, or like the dimension of our statements array, n is going to be between 2 and 15. So that's going to give us a huge clue about how to solve the problem. You might think if n is a kind of a medium-sized number, we're talking about like 10,000 or something, well, then you could think, okay, my solution needs to solve it in n squared time or something like that. My solution can be pretty slow. If it were asking you to solve a problem where inputs are in the hundreds of thousands or millions, you'd know, okay, I've got to do better than n squared. I've got to be, linear, or if n could be really huge, You might think I've got to be sublinear, we've got to be like log n time, something like that. But here, of course, n is up to 15. So that tells you something entirely different. It says that you can use a solution which has what you might ordinarily think of as like a very ugly or very slow runtime. So I see, we're limited to 15. Well, I immediately start to think, can I just brute force this? I don't have to do anything kind of clever algorithmically. So let's talk about that. How would we brute force the solution to this? Well, I think people can either be good or bad. So let's just imagine every possible combination. We know how many people we have. That's the length of our statements list. So let's just imagine every combination. What if person 0 is good? What if person 0 is bad? What if person 1 is good? Person 1 is bad. And we can do a quick gut check. Is it reasonable to try to brute force it that way? Brute forcing it this way means basically that we would have 2 to the n possibilities that we would consider. 2 to the n because for every person can be one of 2 possible people. So if you have one person, that gives you 2 possible worlds. If you have 2 people, it gives you 4. If you have 3 people, it gives you 8, and so on. So is it reasonable for us to try to compute 2 to the n possibilities if n goes all the way up to 15? Well, 2 to the 15 is only 32,000. So yeah, that's incredibly reasonable for us to test 32,000 possibilities. Okay, so that kind of reinforces my belief that we should brute force it. So how do we brute force it? Basically, we generate every possible combination. So we're going to say, what if what if this person's good? What if this person's bad? What if I already spoke through that. We'll generate every combination of good and bad people, and then we'll just check to see whether that combination is potentially valid. And so then we'll filter all of the possible combinations down to all of the valid combinations, and then we'll just find out which valid combination has the most good people. So remember I said that we only care about who is good. So what we'll do is I guess I'll just go ahead and look at the code that solves this and kind of walk through that. We'll only track, who is good. Because we don't need to maintain a list of who is bad. You're bad if you're not in the list of who's good. So let's just walk through the solution here. Starting in line 34 is the function that they asked me to write. And so I'm going to use in line 36 my split method, a method I've defined myself to just come up with a list of all the possible good people. So let's look at the split method in line 23. How this is going to work is we're going to start where result is a list containing an empty tuple. And then in line 26 here, we're starting a loop that goes from 0 to n, which is going to be the size of our list of statements. From 0 to n, we're going to change result, our list that begins with just an empty tuple. And what we're going to change it to is whatever result is currently concatenated with a new list, where the new list is the concatenation of a tuple of the element for every element that's in the result. A tuple of the element concatenated with an element for every element that is in the result. So it's probably clearest if we draw that out. We can just do that for like an input of 2. Okay, so if n is 2, our result list is going to start as just an empty tuple, and we'll go into that loop in line 26, and what we'll say is, okay, I is 0, so I'm going to add a 0 to every element that's already in my result list. I'm going to create a new tuple with the old tuple concatenated with the new element. And then I'm going to combine that with whatever was previously in the result list. So previously in the result list was an empty tuple. Now I'm going to combine that with the result of adding my element to all of the elements that were in the result list previously. In other words, what result will become is an empty tuple and a tuple just containing 0. And then when I becomes 1, for the next execution of the list, we'll do the same thing with 1. So we'll add 1 to the empty tuple, and we'll add 1 to the tuple containing 0, and then we'll combine that with what the result list was previously to get empty tuple, tuple of 0, tuple of 1, tuple of 0, 1. So like that's basically showing us all the possible good people that there are. So either it's kind of like all of the, I'll just leave it at that. It's showing us all the possible members of the good list. Okay, so in line 37, possibles has all of the possible members of the good list. And in line 37, we're just going to filter it down to all of the valid members of the good list. So let's go ahead and look at the check statement, or the check function. And what check is going to do, it's going to take our two-dimensional list of statements and a list of people in the good list. And it's going to tell us, is this valid? So let's look at that function right here. It starts at line 2. How could it be invalid? Well, it could be invalid if a person who we think is truthful, who we think is good, says of another person who we think is truthful that they are untruthful. That would make it invalid. So we say, okay, person 0 is truthful and person 1 is truthful. If person 0 calls person 1 a liar, then we know our situation is invalid. It's not possible for those both to be true. Another way to make it invalid is if a person we know to be truthful says of a person who we know not to be truthful that they are truthful. That would be invalid. And so those are the only two ways to make something invalid. So, we're just going to make those checks. So here we're going to loop through the enumeration of claims. And here, my choice of names is not good because I'm using slightly different names than what the problem used. So, that's just a little curveball to confuse you. Claims is that two-dimensional list of everyone's statements. And the reason I changed the name when I was writing it is just because I wanted to kind of separate the whole entity, like a list of all the claims, from a specific person's statements. So hopefully that'll be more clear in a second. But here in line 6, we're just going to check what I told you earlier. If the person isn't truthful, we don't care what they say. What they say carries no information. So in line 6, if the index isn't in our list of truthful people, we're just going to continue. And remember, continue will just kick you back up to the next execution of the loop without executing any subsequent lines of code. So if they aren't in our truthful list, okay, skip it. We're not going to do anything with them. Go back to line 4. But if the person is in our truthful list, then we're going to enumerate their statements. And here again, statements means the list of statements that the particular person is making about other people. So lines 10 and 11, again, if the person is making no comment, well, that doesn't give us any information. We don't care about that, so just go ahead and skip it. If the person is saying of the person in statement I, if the person, in statement index is saying of the person in statement I, that they are a liar, that they are bad, if the person is saying that they are good, and we don't have them in our truthful list, then we know we're in an invalid situation. So person 0, who we know to be good, says of person 1 that person 1 is good, but we don't have 1 in our truthful list. Okay, this is an invalid scenario. And the other possible way to be invalid is if our truthful person is saying that somebody is bad when in fact we have them in our truthful list. So that would be another way to be invalid. And so then here at line 19, we're basically saying if we've checked every truthful person's statements and they're all consistent, we haven't found any reason to return false, then we're going to go ahead and say true, this is valid. Okay, so those are the two helper functions. So now valid is a list of only the possible configurations of the truthful list that are valid. And so now all we have to do is get the length of each of our valid combinations, and we want to return the most truthful people possible, which is just the maximum value in our length. So, this is not ideal in terms of performance, and I'll talk about that in just one second. It's kind of an average performance. It's at like 58% for speed. There's one pretty obvious minor thing we can do to greatly improve that. So drop us from 2300 milliseconds to 800 milliseconds. And what that is we don't need to test we don't need to check every possible answer to see if it's valid. We just need to start testing at the longest answers. And then as soon as we find one, that will by definition be the longest. So in other words, in this significantly faster version, it's like it's not quite a quarter of the runtime. But anyway, 800 milliseconds versus 2000 milliseconds. What we're doing that's different is we sort the possibles by their length. So we get our list of possible configurations for the truth list, and then we're going to sort it by the length. And reverse true means that instead of being in ascending order, which Python will sort by default, we're going to sort it in descending order. So we'll have the longest possible list at the front, all the way down to the shortest at the end. And then we're just going to go through each of the possibilities, and we're going to check it. And as soon as we hit the first valid possibility, then we're just going to return the length of that possibility. And so the reason why this is much faster is because in the previous version, every time we would check every possibility. And here we just check until we find a valid possibility. That is much faster. And so the final thing I think it's worthwhile to talk about is what situations would you test? Or what kinds of things would you test? Of course, you test both of their inputs. You'd want to look at special cases, like what if everyone was truthful? What if everyone was a liar? What if, the only valid thing, I guess where there were no truthful people, where it was 0 truthful people, or where there are all truthful. You want to make sure you have both the minimum size, where your list is just a 2x2, and the maximum size, where you go up to 15 by 15. And so when I was testing that, to generate this 15 by 15, it's pretty easy. Just, a couple lines of Python in the interactive shell can generate for you random statements, or like a random statement list of whatever length you want. And so then go ahead and plug that in. So that you make sure you can handle size 15. And I don't think there's any, I wasn't able to think of any like degenerate case or any case that would be especially challenging for us, since we're just looking at every possibility and then checking the validity of each possibility. There's no real way, there's no case where we would run longer than what we run in the typical time, at least that I can think of. That's slightly untrue with this, with this version of the problem. But that is true of the first version that I walked through for you. And we know that the second version is worst case, the runtime of the first version. So yeah, I think that's pretty much it. If you enjoyed this, let me know by clicking the like button. If you want to see more content in a similar style, go ahead and subscribe. Thanks for your time. Bye-bye.